Hello everyone, I'm going to present you a paper today. The name of paper is the Formal Module-Driven Discovery of Bluetooth Protocol Design Vulnerabilities. This paper is presented in IEEE Symposium on Security and Privacy in 2022. This paper is actually published by a research group in Purdue. This is the name of the authors who wrote this paper. Before we dive into the paper, let me give you some background information about Bluetooth network standard, which is one of the important network standards that is discussed in the paper. Most of you have used Bluetooth before, either sending a photo to a friend or pair your phone with a speaker. However, the phrase mesh network might not be heard very often, even if they are widely used. For example, if you have seen a smart parking lot before, you can see the parking spot left when you are outside the parking lot, and they will use a red and green light to help people navigate where are the empty spots. Since there are a lot of devices need to communicate with each other, it is not efficient to use the classic Bluetooth to perform the one-on-one pairing among all devices. Therefore, people will use a Bluetooth mesh in this case, which allow all the devices in the mesh network to communicate with each other more easily. If you have a smart device like the Echo Dot shown in the picture or Apple HomePod, they are using the mesh network as well, since they need to control a lot of different devices at the same time. Next, I'm going to talk about the motivation for this paper. Here is a paper for the comparison of known Bluetooth formal verification papers. From 2 to 6, these are the previous works that is working on the verification of Bluetooth security. However, in all these works, they are not discussed about the Bluetooth mesh, and they are not support the pairing mode that is supported by the Bluetooth mesh. Most of them only support for the NC, the numeric comparison, while the others is not verified by these models. Therefore, the author of this paper is trying to extend the previous work about Bluetooth security and extend them to the Bluetooth mesh and support all these modes, the pairing modes that is supported by the Bluetooth. Therefore, they can verify the security property of the Bluetooth mesh and these pairing modes. The next thing I want to quickly talk about is the OOB, out-of-band authentication, since it's related to the attacks that the author discovered. What is the out-of-band authentication? It's basically a two-factor authentication that requires secondary verification method using a separate communication channel. For example, if you're trying to pair your phone with a computer or you're trying to pair your phone with your car, they usually a 6-digit code you want to verify or enter. This is one of the out-of-band authentication. This is actually the output out-of-band authentication. Then I'm going to talk about the threat model that is used in this paper. In this paper, they assume the attacker can intercept, inject, or overhear message transmitted in the Bluetooth channels, which basically means the attacker, there's a man in the middle attacker, they can full control of the message sending and receiving between two endpoints. The other channel is the out-of-band channel, which they assume they will be secured since it is not transmitted using any network channel. The next thing I'm going to talk about is the tool they use to model these protocols. That is something called PerVerif. In PerVerif, you can define a function or like a variable using a let keyword. Like I have a very simple example here. You can just let then the function and its all input and type, or you can just define variable using a let PCA equal to something, and the out and in is something to output to a channel or input to a channel. Uh, it will take two arguments. The first one is the channel, the CH. Then the PCA is the message it's going to send in the channel. There's private and public channel in ProVerif, and you can use model as I mentioned in the thread model. All the Bluetooth communication channel will be considered as public channel, while like the out of band channel will be considered private channel. So here the operation here done in the CH is just a communication that is done in the private channel. These actions can be monitored or injected by the attacker, and so they can send, if they send out anything, the other end might not receive the same thing. They might receive modified message from the attacker. And some fact about the ProVerif. In the ProVerif, they don't have the concrete value. Everything is just a function, just an equation. So you cannot perform like the string concatenation or things like that. You're just trying to model the behavior of the string. For example, if you're trying to do an XOR operation in ProVerif, you need to provide the equation here. So X here is just a bit string, Y here is just another bit string. So X or X XOR Y and XOR Y again will get to the original text, which is X. So this is the equation that help you to illustrate that. The next thing I want to talk about is a case study. This is one of the vulnerability they found in the Bluetooth mesh network. So this is a procedure of the provisioning. Provisioning is a process that when a new device is trying to join the network, uh, they will go through the provisioning process that authenticate the device and exchange some important key for later communication. As you can see in the graph here, the provisioner, attacker, and the mesh device is three devices that will take into play in this procedure. And as we assumed in the thread model, the Bluetooth channel is compromisable, so all the communication can be known by the attacker, and the attacker will be able to send back anything they want. And the first step, step one invitation, there's nothing interesting here, just sending the invitation capability to each other. The attacker just send exactly what is sent by the provisioner and the device to each other. The next step is the key exchange step. In this step, as you can see, the start message sending to the device is the same as the provisioner sent out, but the attacker replaced the key of the provisioner and the device with its own key. So it can calculate the DH key, which will be used in a later phase. And right now, the DH key get by the provisioner will be the one that could be calculated by the attacker. Then the next step is the authentication step. This is the actual step that is being compromised. So in this step, they are using the OOB, the out-of-band authentication, to exchange a number. And in a thread model, this is considered a safe channel, so attacker cannot get the information. These random numbers are kept private to both the mesh device and provisioner. However, the attacker can still watching a message sending from the provisioner and block them to the device. So after the provisioner sends something called provisioner confirmation, as you can see in the equation here. The first two equations is not too important here right now, but the third and fourth one is what we're trying to look at here. In the third step, they are calculating this confirmation value using the Rn, the random number they exchange, and the PRP, which is the random value, the other random value chosen by the provisioner. And the PRD here is the other random value chosen by the device. So there's two sets of random value here. The random value they exchange using the out of band method, and the random value each device pick, like the provisioner will pick a value, the device will pick a value. If you look into the equation, you will realize that the only difference is the PRP and PRD here. If you make it the same value, the confirmation value will be the same. And that's how they utilize these to attack the authentication process. They just send back exactly the confirmation value. Since the next step, they will send back each other the random value they generated to verify that they are receiving the correct confirmation message. In this step, the attacker will also can just reply the same message sent by the provisioner. Since in the provisioning confirmation, they make these two values the same, then it just send back the same random value. So the provisioner will think, oh, okay, this value is correct. I will accept the authentication process. Yeah, that's basically how the attack will happen, and we will talk about the fix in the next slide. There are two possible fixes for this problem. The first one is just checking to see if the random value generated by the device is equal to the one generated by the provisioner or not. If two values are equal, it's highly likely the provisioner is being attacked and someone is trying to join the mesh network. And the other one is more formal one. They are trying to modify the equation. So as you can see in the original equation, the PRP and the Rn is in order for both the device and the provisioner. But if you switch the position of the Rn and PRD, they will generate two different messages, even the random number chosen is the same. So this can be used to avoid the apply attack. Last but not least, this is a result for this paper. In this paper, they are able to use the ProVerif tool to verify 418 security properties, and they detect 82 security violations. These violations are not all causing problems, but they do have the potential to cause a problem in the future. They do find a new vulnerability, which is what I discussed in the case study about the injection in the provisioning process. They find a new security issue, which is related to the out-of-band authentication, and they will also be able to verify 5 known attacks. And this paper is not only finding the attack that I mentioned above, but also give a way to formalize the protocols and be able to model them and verify the security property of these protocols.